Okay, we are ready to start now. Thank you for taking the time out of your busy schedule. I'm Shin Kato, the student of the University of Tokyo. Today I'm talking about Web360square, an interactive web application for viewing 3D audiovisual contents. This is today's outline. First, I will talk about the introduction, our research background, and then I will introduce three methods of 3D sound representation and three interactive 3D audiovisual services. Next, I will talk about my study, Web360square, and summary of questionnaire responses, and finally talk about future work. Okay, let's start. In recent years, the use of video streaming services has expanded rapidly. According to the 2018 Global Internet Phenomena Report released by Sandvine, video streaming accounts for about 58% of all downstream internet traffic. With the continuing adoption of VR services, 360-degree video streaming has also attracted. YouTube, Facebook, and Netflix offer support for 360-degree video and 3D sound. Those video streaming services have applications for web browsers in addition to dedicated applications. The web is an environment that anyone can easily use, and now supports the playing of 360-degree video and 3D sound, for example 3JS, A-Frame, or Web Audio API. But there are a few web applications that can play 3D content interactively. In our study, we designed and implemented a web application called Web360square, which plays 360-degree video and object-based 3D sounds. Various methods exist for representing 3D sound. MPEG 3D audio, which is a 3D audio standard, supports three methods: channel-based, object-based, and higher-order ambisonics HOA-based audio. First, channel-based audio is known as traditional 2.0 channel stereo sound, and there are 5.1 channel surround sound or immersive sound with additional channels. It provides optimal sound performance for a predetermined number of speakers and speaker layout. However, it lacks flexibility and interactivity. Object-based audio uses sound objects which have spatial coordinates, and it renders optimal 3D sound for speakers in real time using those coordinates. In addition, each sound object is managed independently, so object-based can use flexible and interactively. Higher order ambisonics HOA-based audio records a spherical sound scene spread around one point. The spherical sound scene can be easily rotated in synchronization with the listener's head rotation. HOA is also flexible for speaker layouts, but HOA doesn't have clear spatial information, so it's difficult to access each sound object in the sound field. I will introduce three interactive 3D audiovisual services. Inside Music is an experimental website published in 2017 by Google Creative Lab and Song Exploder that uses JavaScript frameworks of WebVR and Web Audio. You can enjoy 3D sound with object-based audio in a virtual space on the web. It is not necessary to install a dedicated application. Only a web browser is needed. In Inside Music, only object-based sounds, not 360-degree videos, are mapped in a virtual space. In our previous research, we designed and implemented STM360square and Vibration, which are interactive 3D audiovisual services for tablet devices or VR head-mounted displays. Both systems were developed using the Unity platform, not web. Here talk about Web360square. We designed and implemented the interactive web application for 3D audiovisual. In the table, we summarize a comparison between the related systems and Web360square. The most important point is the environment is the web. Then the comparison target is Inside Music, but as discussed earlier, Inside Music doesn't use 360-degree videos. Our Web360 Square is published on GitHub pages. The URL is on the slide. This system is built with A-Frame and WebAudio API. Let's give you a short demonstration. When you move the tablet device, the view angle is changed by a gyro sensor. Tapping the front cyan sphere toggles play and pause. You can turn each sound on and off by tapping these audio visualizers. When you turn to the right, you'll hear the sound from the left. If you wear a headphone, it's especially easy to hear. Another content is a concert. This figure shows the overview of system design. The processes in A-Frame are mainly to project 360-degree video on a virtual space and to map audio visualizer onto it. A-Frame also changes the viewing angle. WebAudio API renders 3D sounds in real time and gets frequency data of each sound source. The left figure shows the system implementation. This dashed border field represents the A-Frame process, and this field represents the WebAudio API. The middle field here is for connecting the two fields. The right figure describes the process of an audio visualization. Frequency data is obtained by the WebAudio API on each tick, the order of 60 to 120 times per second. We extract the upper and lower limits of the frequency in which a valid value has appeared at least once, and define this band as the valid frequency band. Then the valid frequency band is divided into 32 groups. The average value is calculated within each group. The audio visualizer has 32 needles that have one-to-one random correspondence to the 32 valid frequency groups. We conducted a subjective evaluation of the Web360 Square through a questionnaire survey that was carried out at Interrupt Tokyo 2019 between June 12 and June 14. We prepared 2 sets of iPad tablets and headphones and accessed Web360 Square on Safari browser. The subjects were 93 visitors to Interrupt Tokyo. First, we provided an overview of the application and explained how to use it. We then let the visitors freely play with the application and evaluate it. After the experience, the visitors completed their questionnaires and we acquired the evaluation data. The questionnaire contained 6 questions as shown on the slide. It was evaluated using the 7-point Likert scale, ranging from 1 to 7. 1 is very poor, 4 is fair, and 7 is excellent. This figure shows the result. The middle of the response of 4 is aligned with the origin of the horizontal axis, while responses of 5, 6, and 7, indicating good evaluations, are arranged in the right direction, while responses of 3, 2, and 1, indicating poor evaluations are arranged in the left direction. As you can see, it is highly rated overall. However, there were not a few poor evaluations for question 3. Question 3 inquired about the 3D effect of the synthesized sound. We believe that this was caused in part by the ambiguity of question 3. It is thought that multiple elements including direction, depth, and spatial realism form the 3D effect of sound. It was difficult to the subject to clearly understand which element the question was referring to, and we didn't know which element the subjects were referring to. Therefore, we will more carefully verify the precision of our questions in future surveys. In the future, we will promote integration with SD ontology. What is SD ontology? SD ontology can describe the multimedia recording metadata in a layered structure. The metadata is, for example, the location information, the orientation of the musical instruments, the venue information, the recording process, and so on. We will promote integration and fetch the metadata used in Web360square from SD ontology. And we also improve and add features and fix bugs on Web360square. In addition, we would like to carry out a network performance evaluation. This is all for my presentation. Thanks for listening.